Oh, hey there. How are you doing? It is Friday, May 15th, and welcome back to Kitchen Table Chemistry. Today's objective is going to be to describe how ionic bonds are formed. Now, yesterday we talked about different kinds of compounds and physical things that we can see about them. Today we're just going to get into how ionic bonds are formed. So, how is an ionic bond formed? And here's a typical ionic substance, and it's sodium chloride. And think of it this way: it's table salt. It is a white hard crystal, and that describes not just the white color doesn't, but the hard crystal part describes most ionic substances. Now, what we have here is a metal transferring all of its valence electrons to a nonmetal so that each element forms an octet. Yes, back to the octet rule. So why do these bonds form? They are going to bring both of the elements closer to an octet, which is more stable, as you'll remember. Again, remember what valence electrons are. They are the outer shell electrons. Metals are going to form cations. Metals are always going to lose electrons. And as you will remember, a cation has lost electrons and anion has gained electrons. So the nonmetals are going to be gaining electrons, forming anions. So metals here will lose electrons. And the nonmetal is going to gain electrons as it forms an anion. These terms need to come back. So opposites attract. Anybody, and I like magnets, and we realize that the like charges repel and opposite charges attract, and you end up with this very, very strong attraction. Now, something to keep in mind, the electrons are locked in place after bonding. Because here we have transfer, the electrons are going to move and they're going to stay there, and that's going to create a very permanent, strong bond. Now, Lewis dot structures. When we draw these things forming, for the next couple weeks here, we're going to be drawing Lewis dot structures. In this case here, we're going to show the valence electrons as dots. In the case of sodium, sodium only has one valence electron, so I'm just going to give it one dot like that, and that shows its final electron. Remember, it's in the S1 um, family. And you might want to actually get your periodic table out for this if you want to just pause and go and get your periodic table. All right, so magnesium here has two valence electrons. It's S2, so it would be 1. And then I'm going to put the other one over here, 2. Aluminum is S2P1, so it has 3 valence electrons, 1, 2, 3. Silicon has 4 because it's S2P2, so 1, 2, 3, and then 4. Phosphorus here is S2P3, it has 5. And we're definitely into the non-metals here. So I'm going to draw all 5 like that. And which side you put the dots on is not so important as the fact you never put more than 2 dots on a side. You can't have more than 2 electrons in an orbital. You can't have more than 2 dots on a side. Each side represents an orbital. Sulfur is going to be S2P4. It's going to have 6 valence electrons. So 1, 2, 3, 4, and then 5, and then 6. Chlorine will be up to 7. And then noble gases, as you would have surmised, have 8. And that'll probably be the last time we mention noble gases because they don't need to gain or lose any electrons to become stable. Okay, this is how you do Lewis dot structures. It just corresponds to where they are in the S and P blocks of the periodic table, how many dots you're going to put with them. Refer back to this and that because this is how we're going to go. All right, now ionic bonding. Huge electronegative differences. So find your electronegative chart. You want to have that electronegative chart to work with here. Remember, electronegativity is the attraction for a shared pair of electrons. And in this attraction, the metal does not have the attraction, and it's the nonmetal that does. So that's going to create this flow of electrons, this one-time flow of electrons from the metal, which is going to form a cation, to the nonmetal, which is going to form the anion. Ionic bonding tends to be exothermic. Energy is released, and when you release energy, what you're left behind is something that is more stable. That energy flows out, heat is given off. I'm going to attach a couple of videos here. You're under no obligation to watch, but the actual combination of chlorine gas and elemental sodium is pretty interesting to see. And yeah, a lot of energy is given off, and it just rains salt. It's cool. All right, very, very short bonds, relative especially to like covalent bonds. These are very, very short bonds. The shorter a bond is, the more energy tends to be stored in it, and the less flexible it tends to be. Ionic compounds are not flexible, and they have very, very short, high energy bonds. Okay, I'm going to show you the ionic bond formation here with aluminum chloride. So aluminum here is going to have 3 valence electrons, 1, 2, 3, like that. And it wants to get rid of these 3 electrons so that it can be like a noble gas. And here we have chlorine. Chlorine with its high electronegative value has 7 electrons. And what we're going to have here is this electron is going to be transferred to chlorine. Now, notice that this is going to satisfy the octet for chlorine, but does not satisfy an octet for aluminum, which still has 2 valence electrons. So we're going to need to put a second chlorine on this, and it can absorb another single electron. And now we have 2 stable chlorines. Aluminum's still not stable, so I'm going to throw yet a third chlorine in there. But you saw where this was going before I got rolling here, and you said aluminum chloride. Aluminum chloride is AlCl3, and that's the Y of it. Aluminum is going to lose all 3 of those valence electrons to satisfy its octet. Chlorine gains each of them to satisfy its octet. So what we have here at the end is we have an aluminum ion. That's our aluminum cation. And we have 3 chloride anions, each of which has a full stable octet like that. So that is the idea here behind ionic bond formation. Very, very short, strong bond. Because the electrons are transferred, they can't flow through. As solids, ionics will not conduct. They're not electrolytes as solids because electrons can't flow through them. As a matter of fact, they're pretty good insulators. All right, what's next? Here's an ionic crystal. Now, one thing to note about this is that every cation is attracted to every anion. So the whole thing is attracted, every positive particle is attracted to every negative particle, and every negative particle is attracted to every positive particle. They're going to set up then in this 3D order. This is called a crystal. Ionic substances are always crystals. That's why it says crystals here. Ionic substances always form crystals. I showed you some lovely copper crystals yesterday, and that you can probably find some examples around your house. But this is what you get. You get this repeating 3-dimensional crystal structure. It will not conduct electricity because there's no way for an electron to flow from one side to the other. Electrons are simply vacuumed up or absorbed into the cations, so it does not allow them to flow. The only way that these things will conduct is if they are molten. So a molten, as in melted ionic, a molten ionic will conduct. That's more like an odd fact. And that a molten ionic will conduct. Am I drawing myself here? No. So a molten ionic will conduct. Otherwise, they don't conduct. And that's like odd fact there. I'm going to put a star next to that weird thing. But it is weird. All right. Now, ionic crystals can't bend. Remember I said that that bond was really, really, really short. Because they're really, really short, if you try to torque it or flex it, you end up with this. That doesn't look very good. You end up with this. Let's go to black again. That's worse, you idiot. Back to the red. Okay. You end up with this negative, negative, and positive, positive. That's not going to work. And that we know that like charges repel. So because like charges repel, this thing is going to come apart. It is going to come apart. That's why these things don't bend. So if you hit an ionic crystal with enough force, it's going to shatter. And it's going to shatter because you're going to set up these areas where it's going to shear apart. And it's going to shear apart because of the negative, negative, and positive, positive interference. So that's why ionic crystals can't bend. Because they just are too short and to take any sort of torque. And that's why they tend to form very hard, very strong structures with high melting points and high boiling points, because these short bonds have a lot of energy in them. So that's why. Do I have another slide here? Okay. Why do they have high melting and boiling points? Because there's a lot of energy needed to break these bonds. The bonds are not going to break until you put a lot of heat into them. Why can't electricity flow into it? Because an electron has no path from here to the other side. It can't flow through because of the effect of the cations in there. So it will not work. They may dissolve in water, but they never dissolve in oil. And they never dissolve in oil because oil is what is called nonpolar. And a nonpolar oil is nonpolar. And because of that, oil doesn't have positive or negative charges. And because we have these positive and negative charges running down the side, that prevents them from ever meeting with each other. The only way an ionic can dissolve in water is if water can overcome the attractive forces of these bonds. And that some substances will, some substances it won't. But we know that that's why we have a solubility chart. Okay, a little bit of an intro into how these ionics work. We won't spend too much more time on this. Please take a look at the attached worksheet. I'm a little into applied information on this stuff, and I hope this finds you well. It's supposed to be a great day, so don't spend too long on this, and then run around outside in the yard and have a great weekend. Take care. Bye bye.